Hello everyone, once again welcome to our physics class. In the previous session we had discussed about Huygens wave theory, and today we are going to explain reflection and refraction by wave theory. How did Huygens explain reflection and refraction with the help of his wave theory? So here we are going to prove the laws of reflection and refraction with the help of wave theory. First we will discuss about the reflection. So the reflection phenomena explained by wave theory. Here you can see two waves. Actually it is not wave, two rays A and B incident on a mirror like surface. It is a mirror, and you know, as soon as rays are incident on a mirror like surface, they will reflect. So we can also denote the reflected rays. So this will be the reflected ray of A, and this will be the reflected ray of B. Okay, now we can mark the wavefront. Once we get the ray, we can easily mark the wavefront. We are considering a plane wavefront here, and the wavefront will be always perpendicular to the ray. Okay, so if we consider a plane like here, see, we are going to discuss or represent the wavefront. So if we consider a plane like this plane is perpendicular to the ray A and B, isn't it? So this green lines represent the plane wavefront, and this plane wavefront is incident on a mirror like surface. Okay, and for our convenience we can do one thing. Let the rays be represented by A dash, B dash, and this point, at the point of incidence, we can mark the points as A and B. So AB is the incident wavefront. That green line represents the wavefront, and the brown line represents the light ray. Wavefront will be always perpendicular to the light ray. So we are considering a plane wavefront AB incident on the mirror like surface. Okay, and here we can mark the angle of incidence. So this is the point of incidence. At the point of incidence we can mark or construct a normal, and this is the angle between normal and the incident wavefront. So let that angle be angle of incidence. So this is the angle of incidence, angle between the normal, and let this normal be N, angle between normal and the incident wavefront AB. Okay, now similarly we can represent the reflected wavefront. So these are the reflected rays, and the reflected wavefront will be perpendicular to the reflected rays. Okay, so if we consider a ray or a wavefront like this, okay, these are the wavefront perpendicular to this rays, and these wavefront represents the reflected wavefront, and we can denote this reflected wavefront as C. Let this point be D. Okay, so here AB represents incident wavefront, CD represents reflected wavefront. Just consider the rays first, after that you can imagine the wavefront there, so you can easily understand the figure. Okay, here also we can mark the angle of refraction. See, this is the point where reflection takes place, isn't it? And this is the angle now here. This is the angle between normal and the refracted wavefront. So let this angle be angle of reflection. Okay, so here also we can consider this as a normal. So two wavefronts are there, AB, which is the incident wavefront, CD, which is the reflected wavefront. We have marked the angle of incidence and angle of reflection. So if this angle is I, by geometry, this angle is also I. And if this angle is R, by geometry, this angle is also R. How is it possible? See, you might have studied one concept in your maths geometry. Angle between two surfaces is equal to angle between normal to that surfaces. Okay, I will just write here. You might have studied this concept in geometry. Angle between two surfaces is equal to angle between normals to the surfaces. So in the figure, just consider this angle. This angle is I, and this is the angle between the line A dash and the normal, isn't it? So I is the angle between A dash and normal. So this is our A dash line, and this is our normal, and I is the angle between that incident ray and normal. Okay, now again, what is this angle? This is the angle between this reflected wave and also the surface. So this line is perpendicular to the incident ray A dash, and this surface is perpendicular to the normal. So angle between two surfaces is equal to angle between their normals. So this is the angle between normal to this surface and normal to this surface. Okay, so here angle between this ray and the normal is I. So this is the angle between normals to these two lines. So this angle also will be equal to I. Here also, if this angle is R, then this angle also will be R. So if we consider here angle between A dash and the normal is I. So angle between normal to this surface. See, the reflected wavefront is like this portion AD. Okay, AD is like this, which is normal to A dash, and our mirror surface is lying like this, and this mirror surface is normal to our normal or perpendicular to our normal. So if the angle between these two surfaces is I, then angle between these two surfaces also will be I, because these two surfaces are normals, corresponding normals to these two surfaces. Okay, so this is a concept that you are studying in your maths geometry portion. Now, you know, as per Huygens principle, each point on the wavefront acts as a source of secondary waves, right? So, if we consider the point A on the wavefront, this point A on the wavefront will generate secondary wavelets. Since this is a point source, it will generate a spherical wavefront like this. Okay, so the secondary wavelets generated from A finally reaches the point B. So the waves developed from A finally reaches the point D. So let the time taken by these waves to reach the point D be small t, and let these waves travel with a velocity v. Okay, so this red color wavelets represent the secondary wavelengths produced by the point A on the plane wavefront, and these wavelets reaches the point D within a time t with a velocity v. Okay, so what will be the distance traveled by these wavelets within a time t? See, you know distance traveled is obtained using the equation distance is equal to velocity into time. So here the waves have traveled with the velocity v and the time is t. So the distance traveled by the secondary wavelets produced from the A to reach the point D is Vt. That is the distance between A and D. Okay, so the distance AD is equal to Vt. Now similarly, B is also a point on the wavefront, isn't it? B is also a point on the wavefront. So this point also generates some secondary wavelets. So let the secondary wavelets generated from the point B reaches the point C within the same time t and with the same velocity v. Okay, so B is also a point on the wavefront. So this point B on the wavefront also acts as a source of secondary wavelets, and the secondary wavelets generated by the point B reaches the point C with a time t and velocity v, with the same velocity. So what will be the distance traveled by the wavelets from B to C? So what will be the distance BC? Again, distance is velocity and into time, and here the waves are traveling with the velocity v, and t is the time taken. So the distance BC is equal to Vt itself. So from this it is very clear AD is equal to BC. Okay. Now here we are going to consider two triangles. Which are the two triangles? One triangle is triangle ABC. Okay, and if we consider here, we have a 90 degree because it is a normal. This is a wavefront, and wavefront will be normal to this ray. So this angle B will be 90 degree. So we are considering two right angle triangles, triangle ABC, and another triangle is triangle ADC. Okay, another triangle is triangle ADC. Here D is also 90 degree because this wavefront is normal to the light ray. So this is 90 degree. Okay, so both are right angle triangles, triangle ABC and triangle ADC. Now in this right angle triangle, AC, the side AC is common to both AB and AD, isn't it? ABC, so AC is there. ADC, side AC is there. So side AC is common to both the right angle triangles. So one of the sides are equal. We can write AC equal to AC. Next, what about other sides? If you consider the side AB of the triangle, of one triangle, and if you consider the side DC of another triangle, how are they? Here we already got the result, that is AD is equal to BC. That is AD is equal to BC. AD is the side of one triangle and BC is the side of another triangle. So the side AD is equal to BC. So another side of the triangle is also equal, that is AD equal to BC. So AD is the side of triangle ADC and BC is the side of triangle ABC. So both sides are equal. Again, if we consider one angle, that is angle B of triangle ABC is 90 degree, and similarly angle D of triangle ADC is 90 degree. Okay, so one of the angle is also equal. So two sides and one angle are similar. So we can apply RHS congruency here. The triangles are congruent, and if two triangles are congruent, remaining sides and angles will be equal. So here I and R are the remaining angles between these two triangles. This I and R will be equal. These are the opposite angles. So from here we got the result, that is BC equal to AD. So the opposite angles will be equal. Okay, so these two triangles are congruent, and if these two triangles are congruent, remaining sides and angles of these two triangles will be equal. So here I and R are the angles formed by these two triangles. So these two angles I and R will be equal. So finally we got the result, angle I is equal to angle R. What does it mean? It means that angle of incidence is equal to angle of reflection. This is our first law of reflection. So we have proved the first law of reflection with the help of wave theory. Okay, how do we apply wave theory here? We considered each point on the wave generates secondary wavelets here, and these secondary wavelets reaches other point within a time t and with a velocity v. So here we have considered Huygens wave theory in order to prove the law of reflection. Okay, thus Huygens explained reflection phenomena with the help of wavefront and also with the help of wave theory. So wave theory is good, or wave theory could satisfactorily explain the law of reflection. Next we can explain the law of refraction with the same wave theory.